Hello everyone, good morning. So welcome back to our winter school. And today our main program is discussing something related to compilers. And our speaker is Amey Karkare sir. So Dr. Amey Karkare completed his PhD from IIT Bombay in 2009 and his BTech from IIT Kanpur in 1998. His areas of interest include intelligent tutoring system, program analysis, compiler optimization, and functional programming. He has more than 7 years of industrial experience, most of which is in compiler optimization. He is an associate professor in Department of Computer Science and Engineering at IIT Kanpur. He was the head of Computer Center and associate dean of digital infrastructure at IIT Kanpur from December 2017 to April 2019. He was vice chairman of GATE Jam 2020 and 2021 for the IIT Kanpur zone. Dr. Karkare received the prestigious Infosys Fellowship during his PhD and PK Kelkar Young Research Fellowship at IIT Kanpur. He has been a visiting researcher at Microsoft Research Redmond and IIT Bombay. Last few years, his focus is on improving how introductory programming courses are taught. He has co-taught large online courses on programming that had the registration of more than 30,000 students. The software he developed has been used at several premium institutes in India like IIT Kanpur, IIT Bombay, IIT Bangalore, IIT Goa, IISER Bhopal. To name a few, Dr. Karkare has also received several awards in recognition of his excellence in the use of innovation and technology to improve the quality of undergraduate teachings. Yeah. So, Abhay sir, you can now start.
Thank you, Avnish. And I would like to say that so my main goal is to make sure we can do effective teaching. Okay, and therefore even for today, though I have slides, I have prepared something. I would prepare if we can discuss, we can interact. Okay, so I do not want to teach you 100 things and then you remember 20 of them. I am more happy teaching you 50 things and then you remember 40 out of them. Okay, I don't think I can teach as effectively that I can teach you 40 and you will remember all 40. So some leeway is there. Okay, so please feel free to ask questions, stop me. I don't know how it will work. Do I have to unmute you, or I think you can unmute yourself and speak up. And when you are not speaking, you can mute yourself back. And you can also post your questions on chat. I will try to answer them. And at the same time, do answer my questions that I will raise either on chat window or speak up one after the other. I mean, I'm teaching a class of 140 students for regular compiler course, but it feels like I am just talking to wall behind my computer. So I don't want that feeling here. So all of you have shown interest in these programs. I hope you will be much more interactive than regular core course where you are forced to do a course. All right. So today we are going to talk about types and programs. Okay, ignore the part analysis. So there is a very nice book by Benjamin Pierce, and most of my slides are based on the work described there. Even if you don't have that book, don't worry, I'm not going to go into very much details of that. Okay. So let me look at dictionary definition of type to start with. So when we say, oh, you are of certain type, or we say that, you are not my type, like you will see in many serials, what it means to have a type. So basically type is nothing but characteristic, common characteristic. So a category of people or things who have, say, a common characteristic, or when you display or exemplify some defining characteristic. So that is the type in general dictionary definition. But what do we mean when we talk about type in programming? So any inputs from you? What do you understand about types in programming? So any answer is correct. Okay, there are no right, wrong answer. There are no marks other than some virtual currency which doesn't have any value, which you won't even get. So answer. Okay. I hope all of you have done some programming. Yes, I don't know if you can. If you cannot unmute yourself, please raise your hand and then I will unmute.
a type establishes the semantics of the
Yashesh Samagar. So your voice suddenly become very low. Yashesh.
Okay, so is it clear now? Is it
Go
clear?
ahead. Yes, now I can hear you.
Yeah, so what I told was, so a type sort of establishes the semantics for the data in question. So for every expression we have a type. The type defines the semantics for that expression, like how should addition operators or subtraction or division should work on the type.
Okay. Any other answer? Because in a way your answer was recursive. You said type means every expression has type. Excuse me. Okay, but I think your idea is correct. Just you could not put forth because the concept is very, very simple. Okay, so let me go ahead. So type is a collection of values. So this is also in mathematics and programming. So it's a collection of values, but then more than that, it is also the operations that are permitted on these values. Okay, so together these two things make a type. And then with programming, we also have what is called a type system, which tells us how to check the correctness of usage of type. So like Yasha said that addition is only allowed on certain kind of types. Okay, let's say numeric types. Plus minus is allowed on floating point numbers or complex numbers and so on. Right. So can you think of some operation which is not allowed on integers? Or can you think about some types where addition is not defined? These are very simple questions, and you can come up with your own type. I mean, let's say structures. Yeah, go ahead. Somebody was saying something, Rahul.
Yeah, so I mean, when you ask, can you think of a type that addition is not defined for that? I don't think there is an answer to that because you can define anything for anything.
Nice. So now you have to come up with a language. So for example, what about C language? Can you add two structures? It does not mean anything unless you define it. Okay. So similarly, I could say that addition on strings is not defined, but then again, I have to qualify it with a language or with some kind of environment. Okay. You can come back and say, no, in Python, addition of strings is defined. Now, what it means is a totally different matter. It is very different from adding two numbers. So that's why I say this type system comes in addition to types, because this is what tells you whether a particular type has been used correctly or not. Addition of two strings in C is incorrect use, but addition of two strings in Python is correct use of type. So basically, type systems tells you about whether a program is consistent or not. So when we look at the world of programming languages, you have typed programming languages and untyped programming languages. So examples of typed programming languages where you have types, can you say a few names? And again, these are freebies. Everyone should be able to answer it. Anyone? You can type your answer on chat window as well. So Pratik is saying int float. No, these are types. I am asking for languages which are typed, which have types. Yeah, C, C++, Java, and so on. Python and untyped. So someone says, okay. So now we are stopping to talk about typed languages. I want untyped languages. Assembly, okay. Any other? Somebody says Python, but I have already typed Python in typed language. Okay. So again, when we say assembly, it's a little bit of it's a philosophical issue whether you consider assembly as typed or not, because even in assembly you have bits which you manipulate and it has some rules. But unlike high-level programming languages, there are not very useful kind of types in assembly. So really, it is not going to be useful for us. The type system of assembly is not very useful. Okay. So now I come to the part which someone has already typed. Python is dynamically typed. Okay. So these typed languages can themselves be divided into different categories, and there are orthogonal categories. You can think of some more categories as well, but here are few important categories. You have languages which are statically typed and dynamically typed. So what is the difference? Statically typed is where your compiler checks for type system, or the compiler enforces the type system. It checks for type rules. It looks at your program and it allows you to run the program only if it is properly typed. Okay. So at compile time itself, you check the types. In dynamically typed, the types are checked during execution of the program. So someone has said Python is dynamically typed. We'll come to that. Yes. And similarly, there is another kind of categorization which is called strongly typed and weakly typed. So Ashutosh has said JavaScript is weakly typed. So I asked him a question. Can you explain what is weakly typed? What is your notion? In fact, I think I have made a mistake here. And it has been long time I have been using this slide, but no one pointed that out. When I looked at Ashutosh's comment, I saw there is a spelling mistake. So I never noticed that earlier. So Ashutosh, what is weakly typed?
One thing, I think in C++ and other languages, type rules are very strictly enforced. In JavaScript, certain kind of illegal type operations may occur. Like there are many examples of string to integer conversions and all that cause problems. So I'm not sure exactly how it's defined, but yeah.
Good. No, your intuition is correct, and the name itself tells you. In one case, type is enforced strongly. I mean, if you make a type error, you are not allowed to run that program. If it is a statically typed language, then you will not be allowed to run that program at all. If it is a dynamically typed language, you will not be allowed to run that program from that point onward. Okay, the moment you make an error in type system, I mean your type system error is discovered, you are stopped from executing the program. In weakly type, you can still continue running the program, but then in a way there are no guarantees. Okay, so strongly typed, statically typed languages where you do compile time check of all the types. So ML, Haskell, Pascal and Java are almost strongly typed. Okay, so Pascal and Java almost, because there are few exceptions where you are allowed to run your program, or a few cases where you cannot do statically typed static type inference, static type checking. So for example, in Java, array bound check is dynamic. Okay, weakly typed C and C++. In fact, they are not strongly typed. I think Ashutosh said they are strongly typed because like C and C++ are very bad languages. You can make a lot of type errors, but still you are allowed to run your program. Okay. Perl is something which is dynamically typed as well as weakly typed, which means you can kind of force any value anywhere and pray to God that your program still runs. Okay. So why all this type system? Why do we have it? Why is it important? Any answers on that? So before we understand, we go ahead. Let's first discuss the importance. So Yasha says less error prone. So yes, anything else? So basically you want to use type system to check for errors. Probably allows more optimizations. I think yes, that is also a correct answer. I don't think that I have that in my slides. the job of compiler becomes easy. Now compiler has additional job of checking the types. So this is a little tricky answer. You'll have to give more details of that. But once again, I will accept it. As I said, there are no wrong answers. You have something in mind, and probably that works. So can you explain, Krishna, how job of compiler becomes easy? I mean, just a high level intuition is fine.
Like what I mean is, we can know what type is before itself in the compile time itself. In the dynamically typed, we have to know it only in the runtime.
Okay, so I think you mean then that the job of runtime system becomes easy. So compiler has to do all this extra work. Yes. So I'm not sure. I don't think we are covering front end of the compiler here. But the job of front end is to check for type correctness. In fact, the middle part of it. Okay. So the back end, in a way, it assumes that your program is type correct. So yes, its job become much more easier when it looks at different kind of types. It knows that front end has verified their usage are consistent, so it does not have to worry about consistent usage of type. So, for example, if you are having what do you say, overloading, then backend will assume that front end has resolved overloading and given you the exact type which is applicable at a given point. So it will be able to select appropriate function for which the code has to be generated, a call has to be generated. So a couple of questions on optimization. Yes, it makes your program faster. And again, if you have a statically typed language, you know that at runtime, there will be very few type checks, if at all. So for example, in Java, generally you only do array bound checks and one or two more checks, but the rest of all are taken care by static compiler. So this also means error detection itself helps in writing safe programs, and it also helps in verifying the correctness of programs. So I think Professor Shubhajit will talk about verification of programs a little bit. So there you will see why type systems are important. It also helps you in the abstraction of the program when you are trying to understand it. So basically it helps in understanding. So if I tell you that, okay, this is an operation which works on integers, many times you don't have to worry about how that operation is actually implemented. Okay. Similarly, if I, for example, think about complex numbers. Okay, if a person does not understand complex number, he has to go inside, look at how addition, division, multiplication, all is implemented. On the other hand, if you know about complex numbers, if I say that this is a library about complex numbers, you will not worry too much about going inside it and looking at all the operations. If you trust me, you will assume how, you will know how to use that library. So it helps in abstraction as well. It helps in documentation for the same reason. Okay, once we know what kind of types we are using, we can simply refer to them, and it makes it easier to understand the program. Maintenance becomes easier. Why? Again, tomorrow if you find out that there is a certain type which causes problem in your system, you can put more restrictions by changing the type rules, and next time you compile the program, automatically any problematic cases can be caught or fixed. Okay, efficiency we talked about. Okay, so these are many of the applications of type-based analysis. All right. So what we will do now? Someone, let me just check any more comments. Okay, so somebody has asked. I will come to that. Less error prone, allows more optimization. This. So how are dynamically typed languages compiled? What if there are thousands of types? Will the compiler emit code for every path? So again, when we say dynamically typed, there are few ground or basic types, and then there are rules to create new types like classes or struct or list or tuples and so on. Okay, so it's not like you can just create a type out of thin air. So will the compiler emit code for every path? Now this part I'm not clear, because doesn't matter which language you are talking about, compiler has to emit code for every path. So Yashas, can you add some clarification? What exactly do you mean by that statement?
So, like in C++, okay, we have some sort of polymorphism, we can have abstract classes, things like that. But in otherwise, in languages like Python, where all those details are not fully exposed and it's so weakly and dynamically typed. So if we now there are tools like Python, right? So they somehow compile it to a binary. So I don't understand how they even work, because if you are compiling it to a binary, you need to like the code needs to be fixed, right? So what if some variable that we assign can take 100, like suppose the Python now can have hundreds of different classes.
Yes.
So there's and since its type is fully determined at runtime,
right?
So the compiler would have to emit code for like, we should assume that like if we have some binary expression, it has to assume that for all combination of types on both sides, LHS and RHS. So isn't that like a lot of code?
Okay. So no, so that's not how it happens. In fact, the compiler is going through every path. It is doing some inferencing, type inferencing. It knows what will be the type of a given expression. There are rules. Okay, so there is type system. It is just that at compile time, your type can be any of those, as you said, yes, the type of X. So I think, let me just open a notepad here. I think probably you want something like this. So can you see a Visual Studio Code screen coming out? You are able to see this black screen, right?
Yes.
Okay, let me see. I would like to increase the size. I decreased it. I think you are having problem because you are saying there might be a code like this. If some condition X, and I'm not writing correct Python, but close to correct Python, some type 1 value, else X equal to some type 2 value, and later I am saying Y equal to X. So these are the, so you're saying here compiler has to generate two different code. One based on whether X is type 1 value, one based on whether X is type 2 value. Is that the problem?
Yeah, sort of, yeah.
Okay. Not really. See, only thing you cannot tell here is whether X and Y have type 1 or type 2 at line 8. Okay. So how do you handle it in an object-oriented language? You have a concept of type which is parent of both type 1 and type 2. Okay. So I'm just going back and forth between an object-oriented language or some statically typed language and things where type will be assigned dynamically. So in a way, you will have concept of a type which is common to both type 1 and type 2, some parent of type 1 and type 2, and you will be able to run this code in statically typed language only if X has that parent type, has that base type. Okay, only then you can assign it to other types. Something similar happens in languages like Python also. See, Python also has this type called object, which is the basic or the the parent of all the types. So in a way, everything is derived from object. So Python is able to also compile this statically properly. Now at runtime, whether you take path 3, 4 or whether you take path 3, 5, 6, actual object of type 1 or type 2 will be assigned to X. And note that if you have done Python, there's a very subtle difference between assignments in Python and assignments in C and C++. Okay, in Python, every assignment creates a new binding. X will point to one memory before the assignment, X will point to another memory after the assignment. But in C, it is the same space. The value changes in the memory. Okay, so in C, you are changing content of a fixed location of the memory when you say X equal to 5, and then later you say X equal to 7. So same memory location gets updated. So X is associated with an address, fixed address. In case of Python, that is not the case. X is pointing to an address and every assignment changes that address. So this is a subtle difference between assignment, the way it works in C++ versus Python. Okay, and that is required because in C and C++, once you define type for X, you know the maximum storage space that is required. In Python, you do not know it because, as you said, user can create a type which is very huge. A user can create a tuple which holds 10,000 values. Okay, so I don't know at compile time whether I have to store 1 byte, 2 byte, 4 byte, or 10,000 bytes. So when you do that assignment, automatically for right hand side, appropriate space is created, it is stored, and a pointer is assigned into X. So we call it reference. Okay, so this is a very high level overview of how it works. Generally, in dynamically typed language, you will see that they do not work with fixed location, but they will work with references, whether it is Haskell or whether it is Python. In fact, Haskell is still statically typed. It does all the statically typed thing, but there still the memory is on this thing in Lisp, I should say, not Haskell. Lisp also you have this, except integers, everything is in dynamic memory. Okay, so let's move forward. No other question? Okay, so again, to make these things, the types role clear, we'll assume a very simple language without any types. Okay, very, very simple language. And I hope you all understand backwards normal form. So I'm saying this language just consists of terms. These are like expressions. Each term can be a constant value called true or a constant called false. I should not say value, it's a constant true. TRUE, or it can be if then else. Okay, you understand this. It means if some term, then some other term, else some other term. And this term can itself be if then else, or it can be true, or it can be false, or it can be a zero, or it can be this kind of operator or function called successor. Okay, so this is a very, very simple language. Predecessor. Okay, so any questions about this language? So what kind of programs can we write? Can someone type out a few non-trivial programs in this language? So 0 is a program in this language, true is a program in this language, successor 0 is a program in this language, predecessor 0 is a program in this language, predecessor of successor of 0 is a program in this language. Okay, so any other trivial, non-trivial program? Someone can type it out. I hope some of you are at least sitting on a desktop so that you can type. Devdan says recursion. So I don't understand what is recursion here. We don't even have function right now. I mean, we have some primitive functions, predefined predicates, but no function. Yes, someone has given a program, if true, then false, else true. I can have if true, then false, else true, else if true, then false, else true, and so on. And even condition can be complex. If true, then successor 0, else successor false, and so on. Okay, so you can create very, very complex program here, right? Now I have given you this language, and I think most of you will be able to, because you have done C programming or Python programming, you have started assigning meaning to these programs. But at this point, I have not told you how my program executes. I have not given you any idea. Okay, whatever ideas you are getting, you are assuming this language is similar to C or Python. Okay, so that's not a good thing. That's a trap. You should always be careful about assigning semantics. You have to ask the designer of the language what is the meaning of this statement or this expression. Okay, but yeah, to keep things less confusing, we'll very soon see the semantics or meaning associated with the programs in this language, and that meaning is going to be very close close to C-like language. I mean, any programming language that you have seen. That's because confusing you is not the aim of this course. Okay, but before that, basically, this is just syntax. So what kind of programs are expected? We saw a few examples. This I spoke and some people typed. So for example, true is a program, false is a program, 0 is a program. Okay. Then if T1 is a program, so when I say terms, I am informally calling it program. So if there is a program T1 which is a correct program in this language, then you can say that successor T1 is also a program, correct program in this language. Okay, syntactically correct. I'm not talking about meaning yet, because remember I'm telling you, don't try to assign any meaning yet. I have not given you rules of the game. I'm just telling you how to create a language. Okay, so it's just like saying in English, a sentence should be subject followed by verb followed by object. So now a sentence like table plays cricket, it is a valid English sentence. Or chair runs marathon, that is also a valid English sentence. However, these sentences are not having any meaning. But again, you will say, I call my friend chair, then suddenly you start getting a meaning. Okay, maybe you have a friend, you just give him a nickname table or chair, then these sentences start getting meaning. So you have to think about semantics associated with program or sentences as well. As such, in regular terms, table is drinking water will not make any sense. But those are proper English sentences as far as just creating sentences is concerned. And similarly, if T1 is a program, T2 is a program, T3 is a program or term, then if T1, then T2 else T3 is a term. Okay, it's a syntactically valid term. Okay, so if you look at any term, it will either be a ground term, which are, I think, okay, now I got it, probably recursion. Recursion, you mean that these definitions are recursive, that term can contain a subterm and so on. Okay, so yes, so here we are. A term can either be a ground term or it is created from some smaller terms. Okay, now the nice part about this is, even though our language is very simple, if you see, your C language also has a similar kind of structure, Python language also has a similar kind of structure, that you grow your terms. Okay, you have some basic terms and then you grow them by connecting them with some kind of operators. Okay, so the advantage of such a definition is that it allows for inductive definitions and inductive proofs. And once again, these kind of proofs, we will be restricted to type systems and very simple type systems, but they are handy when you do real verification as well. Again, I think Professor Shubhajit might take, I am putting a lot of responsibility on him, so he might hate me for that, but he might show you something little complex than what I am going to show. So inductive proof and so on. Okay, if he doesn't show, don't come back to me. I think I have not seen his slide, but I feel he is going to cover some of those things. Or you can ask Avnish, he has also done a lot of such proofs. Okay, so okay, so I say 3 sample inductive properties, but I think I am only showing 2 of them later. So let's say I want to find out what are all the constants used inside the term. Constants mean ground terms, so that I can show you how to create such a definition using induction. Similarly, you want to find size of a term, which is the number of subterms inside it. And you can also talk about depth, which will be the longest chain till you reach a ground term. Okay, so these are 3 proofs, 3 properties, not proofs. So any questions till now? I hope I'm not going too fast. So is my speed okay?
Yes, sir.
Okay. Okay. So I think again for this very simple language, these properties are also going to be simple. And what I want to convey here is, even if you have a very complex language, we have 4 or 5 rules. C language has probably 200 rules. It's just that you have to type more. Okay, overall complexity remains kind of similar, statically at least. So if we talk about constants in a term true, it only has one constant called true. Constants false, it only has one constant. Zero has only one constant. Now, if I want to find out how many constants are there in, or what are the constants in if some else, if then else, okay, or maybe successor of t, I don't know what t is, okay, but I know that this suck is not a constant, it is just a function, or it's a predicate, or whatever it is, okay, it's a primitive function. So the constants which are present in this successor t terms are going to be the same as the constant that are there in term t. You cannot get a constant from outside anywhere. Okay, so this is what we call an inductive definition, or in programming you could also call it recursive definition. Okay, because it's not a programming language, I'm not typing a program, I'm not calling it recursion. So similarly, predicate t, predecessor t, it also has same constants as they are present in t. Is zero, I don't know, I missed it earlier or not. So we are adding this new predicate is 0t, which also has same constant as t. Now this is the one slightly more involved. If t1 then t2 as t3. Now here the constants present will come either from t1 or from t2 or from t3. So the definition is again not very complex. Okay, so I think all of you are able to understand it, right? So this is just definition right now. Similarly, we have definition for size. So size of true is 1, false is 1, 0 is 1. What about size of successor t? Now I'm saying in a way it is a kind of size of number of terms present, number of, I should not call it terms, a number of constructs present. So size of successor of t will be 1 plus size of t, because now we have added one more construct. Okay, similarly predecessor is 0. What about if then else? What will be the size of if then else? Anyone? Size of if t1 then t2 else t3. So my if then else is if t1, let me type it out on chat window, then t2 else t3. So this is what the form of if then else is. So somebody says max of size t plus 1, somebody says max t1, t2, t3 plus 1. See, size, we are talking about number of constructs present in the term. Okay, so in this case, yes, now Yashas has got the correct answer. It is going to be 1 plus size of t1, size of t2, size of t3. Okay, now you will ask, why not 3 plus size of t1 plus t2? Because I am having if and then and else. The reason is here we are, I mean, even though for ease of reading, I am putting them if t1, then t2, else t3, but if then else are together one thing. Okay, I'm not going to have then else somewhere. I'm not going to have if sitting independently in my current language. Yeah, so Yashas has given a compiler oriented answer. If then else is a single node in the AST. That's why we are having 1 plus size t1, size t2, size t3. Okay, so understand this. This is more for ease of reading. I could have written this as if then else t1, t2, t3. T1, T2, T3 themselves are independent of each other. Okay, but if then else is kind of they three either come together or they don't come at all. So that's why we are considering them as a single node in the AST or a single term. And that's why I add plus 1. Again, let me tell you, if there is some other language where these things can come independent of each other, you might have to think about adding plus 3 here. or +2, assuming if then always come together, else can come independently. Okay, but that's not the thing here. That's the designer's choice. What I want to say is it's very easy to write such definitions. And finally, the depth, it's the maximum depth. And now I think what Mayank wrote, or I think what Sayam had in mind will work. So in case of depth, we are not going to look at maximum, we are not going to add up all the depths. Okay. So if you create a tree, the depth will be maximum of any of the branches. Okay. So and then you add one, because once again you are adding one more node like if then else at top of it. Okay. So this is the idea. Okay. Now you will say again, why do all these things? What is the advantage of it? Because these definitions allow us to describe certain properties of the terms. Okay. And again, these properties are very, very trivial right now, but if you have to prove them, okay, you cannot informally prove them. If you have to use some kind of proof assistance, or if you have to write a program to prove them, it's not that trivial. These properties look very, very simple, very intuitive, but I kind of ask you to write them formally. Okay. So for example, one of the properties is number of constants in a term T is going to be less than or equal to size of T. Can you prove it? And how are you going to prove it? Anyone? I need just idea here. First thing, intuitively, does it make sense that number of constants in a term T, so this vertical bars are number, okay? So recall that constants is a set. So the size of that set is always going to be less than size of T. So yes, so quite a few of you know about structural induction. Does everyone know what is structural induction? If you don't, please type no. Okay, so there are few. Does everyone know principle of mathematical induction? Anyone who does not know principle of mathematical induction? PMI. Okay, so I think everyone knows that's class 12 stuff or 9 to 10 stuff. Okay, so what happens in case of principle of mathematical induction? We have to prove certain property E for a number, positive integer, non-negative integer n. Okay, how do we prove it? So step 1, we prove it for 0 or 1 depending on where you want to start. Second, we assume property holds for some integer. Again, I'm not putting all those natural number or integer kind of things, for some positive integer k. And number 3, we prove that using 1 and 2, basically I should say using 1 and 2, we prove that property holds for k plus 1, the number k plus 1. Okay, sometimes there is a slight variation. We say that property holds for all I less than equal to k. Let me just put it also in caps. Okay, so these are two variations, the way you prove property for any. So then we can say that property for all n greater than equal to 0. Okay, depending on where you start, you have to start at 0. So here, let me make it 0. Okay. So again, I just want to say that why does it, how does it prove that just doing these 3 steps that P works for all the integers? or all positive numbers. The reason is, see, we have proven it for 0, and if it holds for k, I know it also holds for k plus 1. So because if it holds for 0, I know it will hold for 1. If it holds for 1, then it also holds for 2, and so on. Okay, so it does not matter how many numbers I have just proven it inductively. Similarly, when we are talking about our program terms, I don't know how complex this term is. If T, then if T1, then T2, else T3. It can be really huge. T1 itself can be deeply nested if then else. T2 itself can be deeply nested if then else. Okay. So how do we prove properties? So in case of structural induction, you prove property holds for ground terms. In our case, 0, true and false. And then you assume it holds for T1, T2, I mean, depending on what you want to prove. So you assume it holds for T, and you prove that it also holds for successor T. Okay. Similarly, for all primitives applications, you have to prove that, assuming it holds for its substructures. So in other words, it holds for this operator T1, T2. It does not matter what is its arity. Okay, substructures. Okay, so this is the idea of structural induction. So in case of numbers, smaller numbers are like substructure of larger numbers. So we do that. Here we anyway have a structure. So in other words, we can say that we prove that property holds for leaf nodes, and then we prove that if it holds for certain internal node, it also holds for its parent node. Okay, and this way you can prove it for entire tree. And in this case, because again somebody talked about abstract syntax tree, you can think about proving properties for AST nodes. Okay, and the once again, you can always convert this structural induction into natural, this principle of mathematical induction, by proving properties using either size or depth. Okay, but you don't have to do that. I mean, the correctness proof for structural induction can be done using proving it for all sizes. But again, so in this case, how will you do it? You will show that, okay, for terms like true, false, and 0, anyway, this property holds. The size is 1, and size of term is 1, and size of number of constant in the term is 1. But for all others, you just assume that the property holds for substructure and show that this property holds. Okay. So any questions till now? Because until now we have just we have created a language, and we have only talked about its structure and certain properties of a structure. Okay, any questions? All right. So now we have to add some more meat to our language. We have to also worry about what does this language do. So we have to talk about values. If I write a program, what is it going to do? So again, for simplicity, it will produce a value. This value can either be a value true, and this is different from that TRUE, true, which we used earlier. But for simplicity's sake, we are using the same constants or same terms. False, or it could be value 0, or it could be successor of v, where v itself is a value. Okay. So note that our language accepts values such as successor 0. It will also accept value. Again, I'm putting parentheses for ease of readability. Okay. Successor of successor 0. It accepts value like 0, but it also accepts value like successor of successor of true. Okay, currently our set of values, sorry, I'm not saying language, our set of values is going to accept such a value as well. Okay, which does not really make sense intuitively, but grammar accepts it. Okay, so somewhere else we'll have to put the restriction that such bad value should not arise, because I don't know what is the meaning of successor of true unless I define it that false is a successor of true. Okay, so now we have to talk about the meaning of the language. Again, I'm not sure if you have done semantics or not, but we will quickly go through what is called small step semantics, small step operational semantics, which is used many times to describe the behavior of a programming language or behavior of any system which can do evaluations. Okay. So what is small step operational semantics? As you can see, small step, it's like one step at a time. So it says that from T to T prime, you can go in one step. We have to give rules for this operation. What does it mean by evaluation in one step? So let's start with very simple and intuitive thing. Suppose I have a program which says if true then T2 else T3. Okay, let's say in C-like language. What does it mean to have such a program? Okay, I know that condition is true, so I should evaluate T2. Okay, I don't know what T2 will evaluate to eventually. Okay, so therefore, this is a small step I am taking. I just check what the condition is. If it is true, then I know that I have to evaluate T2. I can totally ignore T3. And therefore, this whole thing in one step actually reduces to simply T2. Okay. So any question? This is one of the smallest small step. So any question about it? When you go to real languages, you have to have small step for function evaluation, for maybe structure manipulation and so on, which are very, very complex. This is one of the simplest evaluation rule. So if this is not clear, please ask. And this is unconditional. I don't care what T2 is, I don't care what T3 is, I don't care what is happening in the world. Okay, whether there is a war or there is a peace. As long as I have this program, I know that to evaluate this program, I have to evaluate T2. So I can say that the program on the left, in one step, evaluates to T2. Now I will have to think about, look at the structure of T2 and decide about the next step as I will describe. But is this first step clear to everyone? I mean, some of you can type yes or no, especially no. Okay. So if I'm not looking at camera, that means I'm looking at your the chat window. So who can answer? At least one person should affirm yes or no. Okay, thank you. Thank you. So very good. So what could be the next rule? Can you write another rule? Can you someone give me another rule? Any rule, one step rule? Very nice. So, anyone else? I think all of you can see Yashas has given one rule. Now, other than Yashas, any other rule? Third rule? You can also talk about something other than if then else. Okay. So yeah, because after second, third one becomes little tricky. So let's look at second rule, which is what Yashas gave. Now we know that if condition is false, then clearly my program has to evaluate T3. Nice. So Mayank has given another rule, which is also correct. Is 0, 0 evaluates to true. Again, this is unconditional. I don't care what is happening around me. Is 0, 0 will always return true. But what about general if then else? Okay. Now note here, there is some complication. If I don't know that T1 is true or false, I don't know whether to evaluate T2 or whether to evaluate T3. So first thing I have to do is evaluate T1. But again, I don't know what T1 is. Okay, so now I have to do some kind of conditional evaluation. And this is like inference rules you might have done in logic also. So this is premise and this is conclusion. So assuming T1 evaluates to T1 prime in one step. So recall that this arrow means one step. So assuming T1 evaluates to T1 prime in one step, if T1 then T2 else T3 evaluates to if T1 prime then T2 else T3 in one step. So now we are forcing, so a small step is also this nice property, it is deterministic. Okay, it is giving me exactly the rule or exact next step in the evaluation. So here it is, if T1 prime then T2 else T3. So this is one of the slightly more complex rules. Okay, given T1 evaluates to T1 prime, if T1 then T2 else T3 evaluates to if T1 prime and so on. Okay, so what about, so now we can think about adding rule for, I hope you are able to see this small window. So how do I write rule for successor T1 and predecessor T1? Yashas, I don't have any 1 in my language. I don't have any plus symbol in my language. I don't have any plus symbol in my value. Okay, so now you have to come out of C-like mindset. No, my values can only be one of these. True, false, 0 or successor of some other value, one of the success 3. So I cannot just randomly introduce T1 plus 1 or I can randomly introduce a constant. They cannot do that, right? So once again, you have to think in terms of premise and conclusion. So this is the rule for successor. That if T1 evaluates to T1 prime, then successor T1 evaluates to successor of T1 prime. And you can see, even, I mean, that is something which I should not say yet, but T1 prime will have to go ahead and evaluate it once again. Okay, and we'll do that, keep doing that. So even though I am describing only one step, you will keep applying this one step to reach the end value of the program. So similarly, pred 0, and this is natural, let's say predecessor. So pred 0 is defined to be 0. Currently I do not have negative numbers in my language. And predecessor of successor of V is going to be V. Okay. So again, these rules are unconditional. It does not matter. Okay. What is going around and so on. So third rule is where I have to worry about what T1 is. So if T1 is neither 0 nor a value, then I have to evaluate it first and then only I can apply pred on it. Okay. And so on. So I think this is something which Mayank had already told us. And is 0 of any successor of B is going to be false. So these are the steps or meanings associated with the program, how you are going to execute, how you are going to evaluate it. So you can quickly write a simple C program or any other language program to create an evaluator for programs written in our simple language. Okay. Currently, we do not have any type rules. We are just getting the program and executing them. Okay. So now we define few more things. See, there are these rules which are applicable, but there will be time when you may not have any evaluation rule applicable to a program. For example, if I have true with me, there are no evaluation rules. See, evaluation rule requires either is 0 or successor or predecessor or if then else. If my term is simply 0, then there is no evaluation rule which applies to it. If my program is simply successor of 0, again, no evaluation rule applies to it. Okay, go back and check it. Successor 0 is a value. There is no rule which applies to it. If my program is successor true, again no evaluation rule applies to it. So what do we do in such cases? So we call such terms as normal form. Okay. So normal form are in some sense the equivalent of your output of the program. Okay. So to reach normal form, we have to have what is called evaluation sequence. And this evaluation sequence can be finite or infinite. Okay. In our language, it won't be infinite because our language is quite simple. But in general, for complex languages where you have loops or recursive function calls, it can be infinite as well. So an evaluation sequence is just a sequence of term T1, T2, T3 such that T evaluates to T1 in one step, T1 evaluates to T2 and so on. So I think these are quite intuitive concepts. So I won't spend too much time. This is your concept of executing a program. Okay. But then we come to a term called stuck term. A term is said to be stuck if it is a normal form but not a value. Okay. Recall that value in our programs are very few, which is 0, true, false, and successor of another value. Okay, so our value can be of only these form. What if I have my term as pred of true? So this is my term, let's say. Okay, now you can clearly see that it's not 0, it's not true, it's not false, it's not successor of some term, some value. So therefore this is something which is not a value, but at the same time this term is a normal form because I cannot even apply any of the rules. Let's go back to pred rules. So pred either applies to pred 0 or it applies to something which is successor, or it applies to a term which can be evaluated in one step. Okay, now in this case, true is neither 0, true is not successor of v, and true is not something which can take one step. So I am stuck. If my program somehow reaches this state, then I am stuck. And this is where we have concept of error. Okay, so we have a runtime error. Our interpreter or evaluator will not know what to do with it. Okay, so you will throw an error saying that I do not know how to evaluate predecessor of true. So again, this is a simple notion because our language is simple, but in complex language also you have such things. For example, you try to dereference a non-pointer. Okay, what is it? It's a runtime error if you are having, if you are running a C program. If you are running a Java program, probably this error will be caught at compile time itself. Okay, or it will throw an exception if by mistake you are trying to dereference a null reference. Okay, but in our current language, we have no way to catch such errors without running the program. Okay, we have to run it. We have to apply our rules for evaluation, that small step rules, and eventually we'll reach a term which cannot be evaluated any further. So we'll declare runtime error, which is not a good thing for real life systems. What if my program is launching a missile, and after launching the missile, I figure out that my coordinates were computed incorrectly? Okay, so again, I'm giving some kind of a very extreme example. So you launch a missile and you figure out that the coordinate system was stuck to null and the missile is coming back to the base station. So you don't want to do that. You want to verify your program. You want to check it for existence of such error without actually running it. Okay, and this is where you add types to the language. So any questions till now? So all this was to emphasize the need of type system. Even in our simple language, we need it.
The example that you just gave,
Yeah.
Yeah, that, I mean,
Predecessor of true?
no, not that. The The missile one.
Missile one, yes.
Yeah, that okay. I mean, isn't that a matter of performing proper checks before doing something? Like,
Of course, of course. Now, I mean, you have to sanitize your inputs, right?
yeah.
Yes. So that can be at one is at dynamic time, but similar things you have to do at run compile time as well. Okay. You will think that okay, this example is not good because at types with types only I can do static checking. But what if you are adding two floating point numbers and you know that your precision is not good enough? I mean, you should look at this. I mean, if Shubhajit is there, he can remind me of name of that aircraft which crashed. Adrian, right? Avnish, you remember? So in fact, it has happened that some rocket was launched and it crashed because they were computing numbers which were 32-bit and they were storing it in 16-bit or something like that. Okay, so yes, as I said, my example may not be perfect for the case, but you have to check for overflows, underflows, and other things in safety critical system, and that can be done using types. The example I have given is not really far-fetched in that sense. It has happened in real life. You look for, I think it's called Adrian rocket disaster. I will search for it and share the screen. Okay, Ariane 5, yeah, not Adrian, Ariane 5. So thank you, Sujit. Okay, read about it. And similarly, there was another case of Thirak 5 incident. I don't know if it was also 5. Thirak, where you had a medical machine to inject what is it called? So for cancer patient, you were giving some kind of therapy, this nuclear therapy, not nuclear, what is it called? Dosage of again radiation. Yeah. So
Chemotherapy.
yeah, so radiation therapy, and again due to some programming error, these patients were given 1,000 times more radiation than necessary. Okay, and it created a lot of hue and cry because many patients suffered from these nuclear issues after that due to this radiation exposure to radiation. Okay, so these are not in that sense or far-fetched scenarios. Okay, so again, not everything can be done using simple types. There are other verification, but what I'm trying to show is just a motivation. Okay, so let's add two kind of types to our language: bool and nat, which is natural numbers. Okay, so note that we do not have concept of 1, 2, 3, 4 as we see in our regular programming language. Again, this is not a practical language; it's more of a toy language for studying. Okay, but you can add things to that. And now before running the program, actually evaluating it, I do want to have some kind of type checking. So I want to add type rules. And again, these rules will be assigned or designed by the developer of the programming language or the designer of the programming language. Okay. So here we have this symbol called turn style. So once again, this is very similar to saying there are some environment and then you are making some inference. Okay, so when I have this turn style followed by T colon capital T, it denotes term has type T. I mean, irrespective of anything. Sometimes we'll put some constraints before the turn style. So now we add type systems, and again, any type system you work with, it will have types for ground terms. See, somewhere you have to start. So you will tell your compiler, okay, 0 has type integer or 0 has type natural number and so on. Okay, similarly, something within double quotes has type string. So those basic information you have to give, and you have to also give some rules which says, for example, if I have a natural number T1, then successor T1 is also going to be a natural number. Same about predecessor. If T1 is a natural number, then is0 T1 is going to be a Boolean. Now note that we are not talking about the values here. We are only talking about what will be the resultant type. Okay, and in a way you are telling compiler what kind of sentences are valid. Even though they follow the grammar, there are certain sentences which will not make any sense. So true is Boolean, false is Boolean. If T1 is Boolean, note that T2 can be any type, but T3 has to be same type as long as this condition holds. Then if T1, then T2 as T3 has type T. Okay, so this is again an inference loop. So earlier everything is this is your axiom. These are all inference loops. Okay. So now we look at them and then we define the relationship, which is the relationship between terms and types. So basically it's nothing but the big words for saying that every term should be assigned a type, and that relation is there. Okay, using the rules which we have discussed just now. And we call a term typeable or well typed if you are able to find a type for it. Okay, so even in languages where you have to declare explicit type for variables, you still have to decide type for expressions. Okay, so don't think that languages like C don't have to do any kind of type inferencing. The job is easier because you specify types for many of the constructs. But at the same time, if I have E1 star E2, the language still has to do some kind of manipulations of types to figure out what is the result of multiplication. Okay, and when you are doing proofs, you need inversion of typing relationship. Basically, again, we are not going to do much proofs here, so I will not spend too much time. But the idea is many a times when you are at a certain stage, suppose somehow I reach a stage where someone says 0 has type R, then I can quickly infer that R has to be net because that's the only allowed type for my 0. Okay. Similarly, if T1, T2, T3 having type R, then based on the rules, I can quickly infer that T1 has to have type bool and T2, T3 both have to have type R. Otherwise, my type system is not consistent. Okay. Now, one more thing here. This type system is for very simple language. We do not have overloading. We do not have polymorphism and other thing. When you have all those advanced features, you have a type system which will be a little bit more complex. The inversion of type relationship will give you the most generic type in some sense. So it could happen that 0 behaves like floating point in certain scenario, it behaves like integer in certain scenario. So you will have to have some kind of a notion of a numeric type which can behave like both float as well as int. So you can only infer 0 has type int, or you will need more constraints, 0 has type numeric, and you will need more constraints to figure out should you take it as int or float. Okay, but those are complex things we are not going to go into in this introductory kind of lecture. Okay, but this inversion relationship is very, very useful when you go for proofs, proving that certain term has certain type. Okay. Now, in our language and our type system, every term will have at most one type. The type is going to be unique. And again, because of that very simple rules and very simple types, there is just one derivation. Okay, so all these is given by this language. So now we come to the main thing. Our goal is to make sure when we are running a program, it doesn't reach a stuck state. Okay, it doesn't reach an error state. So the type system that we have given till now, it is called, it is a safe type system. Okay. So what does that mean? Any term which gets a type in our type system, you will never reach a stuck state. And that can be again proved using two sub properties. One is called preservation, one is called progress. So let's look at these two properties. Okay, together this whole thing is called that well-typed programs do not go wrong. And I'm putting go wrong in quotes. What it means is what you have written in the program. If you have a strong type system and your program passes type checks, then your program is not going to produce a stuck state or a unwanted scenario like accessing a null pointer or so on. Okay. But again, assuming those rules are there in the type system, right? It does not say that your answer cannot be logically wrong. Okay, if I have to add 5 and 2 in my program, 5 plus 2, by mistake I write 6 plus 2. Now the program is going wrong. It is producing 8 when it is supposed to produce 7. However, note that this incorrect thing is with respect to your notion of some external knowledge, okay, that you wanted to add 5 and 2. What you wrote in the program is 6 plus 2. So in that sense, your program is not wrong. You were supposed to call square root function. By mistake, you called SQR function or square function. Okay. So again, your output will be not what you expect, but that does not mean your program is wrong. It is what you have typed is not correct with respect to your other requirements. Okay. So understand this. Type correctness does not mean logic correctness. It just means you're not going to do certain operations which are dangerous, or in our simple language, which reach a stuck state. Okay. So what does progress says? Progress says that a well-typed term is not stuck, which means if you have a term which is well-typed, it is either a value or you will be able to take one step of evaluation. So if t is typed, then it is either a value or there exists a t prime that t can go to t prime in one step. Note that this is very, very important. This says either you have received the value, your program is terminated nicely, or you can still take one more step. Preservation says if you have taken a step from a well-typed term, then the resulting term is also going to be well-typed. I mean, it will not happen that you evaluate successor of 0 and then you end up getting a term which is if something which cannot be executed. Okay, so if t has a type and t derives or t evaluates to t prime, then t prime, and again in our simple type system, t prime will also has that same type, capital T, exactly the same type. But then if you have complex type system, complex types, then you can have T1 here and T2 here for type. But note that again, these two will be related somehow. It's not, it's very, very unlikely that you start with a Boolean and end up getting a structure as a result. Okay. So these are somehow related. I mean, it could be one of the components of a tuple. It could be some kind of a derived type and so on. But it's not going to happen that you do x plus, 5 plus 3, and then you end up getting a string called hello world. So this is all the thing. And now you can see together progress preservation. What do they tell you? Assume you start with a well-typed program. Either you start with a value itself or you will be able to take one step. But then this one step also has a well type. Okay, it is well typed. So that means either this t prime is a value or you can again take one more step. Okay, and so on. So that means you are never going to get stuck. Once again, this thing does not guarantee that you are not going to end up in a program which loops infinitely. Okay, so if your program has loops or recursion, type system will not guarantee termination. What it guarantees that either you terminate or you are making some progress. Okay. So this is all I wanted to cover. I think I've done good in time. So any questions? Okay. I have used deliberately very simple language, and it's also part of that book by Type Systems by Benjamin Pierce. Okay, and to make up for that, I am giving you a language, slightly made up language, okay, for which you have to write type system, and it is much more complex than the one which we have seen. So here is a language for file IO. Okay, so here programs have some declarations followed by statements. So declaration is a list of declarations. Statements is a list of statements. Each declaration either declares an integer variable or a file variable. And your statements are one of these 5. You can open a file, or you can close a file, or you can write to a file. Note that here V1 has to be a file and V2 has to be an integer. You can read from a file. So v1 has to be an integer, v2 has to be a file, and you can also assign one integer to other. So very simple language which does things with file IO. It again, if you look at it, it's not very practical. I had to keep it very, very small. And I will share this as a PDF with Professor Shubhajit, and maybe I will add few rules. This uses things which are not covered in the class, but again, this is more of an exercise, and I will also share the solutions. Okay. So for simplicity, we are not giving file names and other things. We'll assume that somehow variable will get associated with a file variable, and also that we are not showing anything how these variables are formed. So you assume that there are C-like variables. Okay. So these are the type constraints, and please read them and understand whether they make sense or not. So what I want from my language, I have not given semantics, too much semantics, but again assume C-like semantics. So a variable should be declared only once. So these are the type rules that I want to capture. A variable should be declared only once. All the files are closed at the start of execution. They are also closed automatically at the end of execution, if not explicitly closed by the program. Opening a file is compulsory for performing any read or writes, but you cannot open a file multiple times. Closing an open file will close it for read and write. Any further reading, did I say opening an already file is not, opening an already open file is allowed. So I can keep opening it. If I don't, I'm not sure whether it is opened or not. So any further reading and writing on a closed file will be an error. So closing will close it completely, no matter how many times you opened it. So it's not like a matching the open and close. So you open a file 100 times, the moment you close it, it's gone. So you can reopen it to read again, but you cannot just simply read from it. And secondly, closing a closed file is not allowed. Again, you can see these restrictions are not very what you can say, very, very rational, but they are more to make you create rules according to type system. And other thing is reading an open file returns an int, and similarly writing can only happen to an int. I mean, to a file you can only write an int, and you can only assign int variables, but you cannot assign int to a file or file to int or file to file. Okay, so these are the type rules. So you have to add a type system. So you have to add types. So you can have int type, which is given in a way file type. Then you also need a type like valid, error, and any other type that you think you might need. Okay. So what we want to say is a program is valid if all the statements in this program are valid. And we want to design a type system to capture the constraints described in the previous slide. Okay, so in particular, you need to describe some axioms and inference rules for various constructs, all the constructs that I have shown here. So constraints have to capture these rules. And now there is something which we have not done in our language because we did not have a notion of variable declaration. So you need to have a concept of type environment, which will hold types of variables, file variables, and it also needs to hold which files are open, which files are closed. Okay, so this is something in a way has to be written like this. So suppose I am handling this declaration int x. Okay. So initially I might have my empty set, but after I see int x, okay, I need to have a set which contains this information that x has type int. So this is what I am calling gamma, type environment. So initially it is empty, but after I have seen this declaration, I should include x says int in my set. So initially, if it is y, it has type float, or I don't have a float type, so y has 5. Then after this, it will become y:5. Okay. So in general, if my initial environment is gamma, then my final environment will be X colon int union gamma. X equal to, let's say 5 or whatever, maybe x1 equal to x2. Okay. In this case, I need to check x1. Again, I'm using slightly loose notion that, but you can also use loose index, that x1 belongs to gamma, x2 or x1 colon int belongs to gamma, and x2 comma int belongs to gamma. Okay. Only then this statement will make sense. So this has to be a premise, in which case conclusion is x1 belongs to x2 has a valid type. Now you have to come up with the, you can write it in English as well. Okay, so because we have not done these inference rules in lot of details, but you can use something like this, comments as well as sentences. Okay, and I will share one possible solution to it maybe tomorrow sometime. Okay, so I open the floor for queries, questions, and let me also search for story about Orion 5. So this page does not talk about its crash. Oh, there are multiple, that's why. So just let me see. So 40 seconds after the launch, it crashed. And so there was some error in the software, and somewhere it should tell that why it happened. In this case, it's not there, I think. Okay, so thank you, Sujit. So Sujit has shared a link on the things on the chat window. Yes. So 64-bit floating point, but somewhere they tried to fit it into a 16-bit variable. Okay. Now, once again, we become knowledgeable after things have gone bad, and people have started adding these kind of type checks that whether you are having overflow, underflow or not. Okay. And similarly, I think the other one is Thirak. Accident. Thirak 25. Six accidents between 1985 in which patients were given massive overdose of radiation. Okay, so once again, I don't think here the cause was a floating point error. So, but again, it was a software bug. In this case, it was some kind of ordering between the setting up values. So setting a later value was resetting the previous value, but again, they could have checked the ranges of values. See, nobody should be given that much radiation. Okay, so maybe they could have put some type check saying that the value of radiation should not be more than certain values, or they could have only used enumerated values for radiation. So like that. Okay. And again, it's easy to say these after we know the cause, but I mean, this is quite old thing, 85 and 87. People were not so much concerned about software correction, maybe in those days, software verification. So we are 5 minutes past the allotted time, so I will stop there.